Welcome back to another Houdini tutorial from 9between, and in this tutorial we recreate this Thanos portal effect from Avengers Infinity War. Also, be sure to check out our blog post linked below if you need further help with this tutorial. So, to start this effect we create some starter particles that shoot out from the center. We then create some curving particles using a pop curve force that swirl around. We then create a pop network that controls our light emission, and then, using a Houdini digital asset, we create some lightning. Finally, we turn that all into smoke, and then we render it out. And yeah, hope you enjoy. In Houdini, we can begin by dropping down a geometry node. We can rename this file to setup, and then dive inside. So, for the general shape of this, we'll firstly need to drop down a circle, give it a radius of 3 by 3, and then where it says primitive type, we'll just change this to a NURBS curve. Next, we'll go ahead and change its arc type to an open arc, and if you set your points, you'll be able to see that we don't have many points to work with. So let's drop down a resample node, and then resample by maximum segment length. So that's perfectly fine for now. Then we can go ahead and drop down a transform node, and this is what's going to define the animation of our circle. And to do this, what we need to do is just reduce the size at frame 1 to 0.01, Alt and click on Uniform Scale, and that will set a keyframe, and you can tell by that green marker that's placed on your timeline, as well as the now green value in this channel box. So now we can go ahead and jump to frame 96, and then set this to 0.75. If we play this back, you'll notice that it grows, and it's growing too fast because we need to activate our real-time toggle, which plays it back not as fast as possible, which is the default, but rather it plays it back at the right rate, so 24 frames per second. So there we have our general shape. Next, we can go ahead and drop down a polyframe. Now polyframe is very useful for figuring out tangents and bitangents, and we've used this before in the other portal tutorial, but for this one we're going to do something slightly different. So if you activate your normals, you'll notice that they're pointing in the negative Z direction. What we would like is we would like them to be pointing away from the center. So to do that, deactivate your normal name, deactivate your tangent name, activate bitangent name, and change this to N. And now you can see that they are pointing outwards, away from the center. And if we convert this from a normal value to a velocity value, just by changing this to V, and then setting our point trails, so now we have velocity that's pointing outwards, and that's great. So what we can do with that is now add some noise to this velocity. To do that, we can drop down an attribute noise. Now attribute noise is extremely useful if you do not need an attribute VOP because you do not need a lot of control, and you can actually do great things with an attribute noise VOP. So we'll be using an attribute noise. Remove CD from the attributes that we'll be affecting, and the attribute that we will now be affecting is V. We will like this to be multiplicative, so activate it there. We'd like this to be animated, and we'd also like to remap this from 0 to 1. So now we have a noise value that multiplies our V value by a random value between 0 and 1. If we activate our point trails again, you can see that they are now a bit jittered. So we'll just decrease the size of this to 0.2. Next, we'll go ahead and keep adjusting our velocity by dropping down an attribute Wrangle. And in this attribute Wrangle, we'll do a few things. Firstly, we'll create a Flirt Timer. And this timer will be equal to our current frame, so at frame, divided by, and I worked on a frame range of 168 frames. You can work on 240, but for the sake of this tutorial, we'll do 168. And then you can go ahead and say V at V times equals rand at ptnum, so each point will get a random value, multiplied by 7.5, multiplied by channel ramp, we'll call this time underscore mult, and then we'll drive it by timer. Close that, create your spare parameter, and what we're going to do is bring up this first point, drop the last point, and add a middle point. So bring it about a quarter of the way through and bring it all the way up. So if we play this back now, you'll notice that we have very high velocity initially, and it slowly tapers off. Now we want this frame range to only end at 168 because that's where our timer ends. So now we have this tapering off over time, and that's perfect. So now we can go ahead and scatter some points. So we can drop down a scatter node, and we'll scatter 1000 points. Then we'll also drop a point jitter, just so that they're not all on top of each other. Jitter this by 0.1. Great. And now the next thing to do is to drop another attribute noise. This time we're going to be creating an attribute as opposed to affecting an existing one. So we will be using additive. This time it'll be one-dimensional, and we'll create an attribute called remover. So it will be animated, we'll use simplex, we'll remap this to 0 to 1, pulse duration of 0.3, element size of 0.3. So now, if we drop a delete node, we can delete based on that remover attribute. So change your entity type to points because we're working with points, delete by expression, and then just say @remover less than 0.5. And now if you play this back and switch off your point trails, you'll notice that these points flicker and jitter. So this is useful for adding noise to our pop network, which we are now going to create. So drop down a pop network, plug this into your first input, and then we can dive inside. So on your source first input, go ahead and just change this from scatter onto surfaces because we don't have a surface anymore, but rather we have points. So we want to emit from points from our first context geometry. Now we can go over to birth, and we can change a few things here. Firstly, we'll only set a constant birth rate of 100. Next, we'll go over here to our life expectancy, change it to 0.2 with a variance of 0.1. So now our points will last anywhere between 0.1 seconds and 0.3 seconds. Great. Now we can go ahead and drop down a pop wind. And we'll give this an air resistance of 0.5, an amplitude of 1. If we play this back, we now just have these points being shot out. Now what we'd like to do with these is give them a group. So we'll drop down a pop group, and we'll give this a condition. So enable over here where it says rule. So we can just click over here in our vex expression and press Alt and E, and that'll bring up our string editor. Next we can go ahead and just say if length v at v greater than 2, then put the point into this group. So if our velocity's magnitude or length is greater than 2, then do the following. Now, you may be wondering how that works. Now, velocity is often positive or negative, and to actually find a value that's absolute, where positive and negative doesn't matter, but rather the magnitude of the strength, we would rather use this length function, because what it does is it adds x squared plus y squared plus z squared, and then square roots all of it, and you end up with a positive value. And depending on how strong your velocity is, it will be a higher or lower value. So we can apply and accept, and then we can go ahead and just give this a name. We'll call it fast group, and then drop down a pop replicate, plug it in after your pop group, and the group that we will be replicating is our fast group. Now we need to just change a few things on here. So what we'll do is give this a constant activation of 30,000, change its life expectancy to 0.5 with a variance of 0.3, and we need to change its shape. So go from sphere with a uniform scale of 1 to a sphere with a uniform scale of 0.3. Next we can go ahead and add to inherited velocity. So we only want an inherited velocity of 0.2, and then we want variance of 0.1 on each axis. So now we can play this back. As you can see, you end up with these large clumps of particles being pushed outwards. Now, what we would like to happen is for these particles to be pulled back in towards the center. So what we can do is after our merge node, we'll just drop a pop attract. Now pop attract attracts particles to a certain point. That can be a geometry or that could be a position. In our case, we're going to pull it back towards the origin, so position 0, 0, 0. So we go over here, leave this as is, we go over to force, accelerate, and we'll give this a force scale of 6. Now if we play this back, you'll notice that these points are getting pushed out and then pulled back in. Now the last thing to do with this is to just copy over our source first input, plug it into this merge node, and increase the constant birth rate on this one to 100,000. And as you can see, it's shooting these particles too far out. So what we'll do is we will add to inherited velocity just 0.5 with a variance of 0.1 on each axis. Now if we play this back, we end up with this line that's created that's constantly emitting. And you can add more variance to that, maybe 0.5 on each. And that should be fine. Now what you may notice is that it's shooting out these large clumps of particles for too long. And the reason for that is on this attribute wrangle. So we can just add another point and pull it back over here and pull it down so that it's a faster fall off. So now our velocity will fall off a lot faster. So if we play this back again, you'll notice that it no longer emits those. Great. So that looks pretty good. We can just add a pop wind to roughen this up. So go ahead and drop down a pop wind and just put it after your pop attract. We'll do an amplitude of 1, a resistance of 0.5. There we have it. Now that we have that in place, we can go ahead and drop down a null, and we'll just call this null starter underscore particles underscore out. Great, so now we can go ahead and just grab everything until our polyframe and put this into a network box. Now we can drag it around and we can minimize it. So the next thing we're going to do is create that swirling particle effect around the outside. To do that, we need to firstly drop down a time shift node. And what we're going to do with this time shift node is clamp to first, right click on start end frame, delete channels, set this to 30. So now it freezes frame 30 for the first 30 frames. Now we can go ahead and drop down a poly wire, set this to a wire radius of 0.2 with 7 divisions. Then we can ISO offset this, so turn it into a volume, and to give it better definition, change your sampling divisions to 50. Next we can go ahead and drop down a scatter node, and this is just to scatter points into our volume. And we're going to scatter 10,000 points into this. And we're going to switch off relax iterations so that it computes a bit faster. Next we can go ahead and drop down our pop network. Take your scatter into the first input and take your time shift curve into your second input. Activate your display flag, dive inside. Now we're going to be doing a few things in here. Firstly, we're going to adjust our birthing. So go over to your source on your pop source first input, and instead of scatter onto surfaces, once again we'll use points. Go over to birth. So now we would like to keyframe these particles so that we have more particles being emitted towards the latter part of this effect. Because keep in mind, this is the swirling that's only seen towards the middle and end of the effect. So we can go down here to this image of the brain and just click on that. That'll disable your simulations. So now you can go through your timeline without anything simulating. Go to frame 1 and we'll just set our constant birth rate to 0, hold Alt and left click on constant birth rate. Next we'll go over to frame 48, and over here we'll set a constant birth rate of 50,000. Alt and left click once again to keyframe that, and now we're going to go to frame 72 and set this to 1 million. So 1, 1, 2, 3, 1, 2, 3, 1 million. Alt left click. Now 1 million may seem a lot, but keep in mind that this is the number of particles emitted every second. So over a period of 24 frames, this is how many particles will be emitted. Now we have a life expectancy over here, and remember, life expectancy, this is in seconds. So if we set this to 2, then the most particles we'll have is about 2 million. And we can set our life variance to 1, and now it'll be anywhere between 1 second and 3 seconds of life expectancy. So we can go back to the beginning, reactivate our simulation, and now we can go and create our pop curve force. So drop down a pop curve force, and we're going to put it after the merge node because we're going to be feeding in another stream, and we want it to also be affected by everything after our merge node. So pop curve force fetches a curve. So firstly we're going to give it a curve, and we'll be using our second context geometry. That's our time shifted curve. Now a pop curve force does a couple of things. It adds forces depending on the shape of a curve. So in this case our curve is a circle. So we have follow scale, suction scale, and orbit scale. Now, follow scale defines how quickly a particle travels along the curve. Suction scale defines how much particles are pulled in towards the curve. And orbit scale defines how much rotational force is applied around the curve. So what we're going to do is firstly change our max influence radius to 1. So that's basically just reducing the size of this. And then we're going to have a follow scale of 1, a suction scale of 2, an orbit scale of 3. So we'll have particles slightly following the shape of the curve, they'll be pulled in quite a bit, and then they'll be orbited around the curve quite a lot. Now we're going to go over here to these curves, and we're going to remove all of the points so that all of these are just equal to 1. So just remove this last point, and do this for each of these. And the only thing that we're going to change on velocity force falloff is we're going to set its constant value to 0.3. Now the reason we're removing falloff is because we have a circle, and we don't want it to be noticeable that there's actually a break in our circle. So we're removing all falloff. And there's one more falloff we need to remove that's under global forces. This is force along length. So if you don't remove this, you'll notice a slight point where there's less force. So we just need to remove this last point, and that'll be just fine. So now if we play this back, you'll notice that our particles are being flung quite far out and away from our actual curve. Now the reason for that is because we don't have air resistance. Air resistance basically forces the particles to move a lot slower, and it dampens their velocity every frame. So we're going to add air resistance by dropping a pop wind. We're going to be putting this after our pop curve force because we want our curve force to be the main effect, and then our wind to just add to it. So now we're going to set an amplitude of 2 for noise, and you can actually see what this does already. Now our particles stick quite closely to our curve. Of course there are a few still being flung out, but that's okay. So as you can see, it goes quite slow, and that's simply because we have a lot of particles. But that looks decent. I think the only thing that I would recommend changing is maybe the size of this. So you can change the size on your pop curve force over here, you have shaping over here. We won't really change that, but we can change our global forces. We can increase our max influence radius and give that a go, and that keeps it more in check. So the next thing that we're going to do, we're going to add some wind velocity on our pop wind, and we're going to add it in the direction that this is rotating. So if you take a look, it's rotating out towards negative z and then back towards positive z. So we want wind pushing backwards, and that will be towards positive z. So positive z will add wind velocity of 2. Play this back, and you can see what's happened. Some particles are now being pulled out towards the back of this. Now this is quite important to get right, because this is actually going to define how our effect looks. So we want this to be as accurate as possible, and we want enough particles to work with. So I'm going to make a few changes, going to go up here, and I'm just looking at this now. I think we can maybe increase our polywire size to 0.25, and maybe increase the amount of points that we're scattering to 12,000. So now we can play this back. And I think that looks pretty good. And we can take a look at how many particles are actually being generated on here by holding the middle mouse button on our pop network, and it will bring up some information. We have 1.2 million particles, So this will probably range between 0 and 1.5 million, which isn't actually that much. Oftentimes you'll go up well above 10 million. Just depends on the situation, but this should be fine for what we're going after. Next, we can just drop down a null, and this one we'll call curve underscore particles underscore out. And what we're going to do is we're going to file cache. So drop down a file cache node, and I'd actually like to file cache both of these separately. So we're going to, just before our null, add a file cache node to our curve particles out, and then we're going to find a place to save them. So let's just go and find a place, and we're going to just call these curve particles tut.f.bgeo.sc. $f just ensures that we're saving every frame, and .bgeo.sc is just a really good way of saving things in general. When you're caching things out, you can save as .sim or .vdb, but each one of those are very specific. Like .sim will result in huge files, but they allow you to continue your simulation from where you left it off. And .vdb would be useful if you're saving out some smoke, but all of those, it depends on the situation, but .bgeo.sc is generally a good way to save your geometry from a file cache node. So accept that, and then we can say save to disk. And this might take a little while, because we're actually generating quite a few particles. I'll be back when that's done. So once that's finished caching, we can go over here, set your display flag, and go load from disk. And then you can play this back, and it'll play back a lot faster. So that looks decent. I'd also like to just save our other particles on this side, so we can drop another file cache node. And over here, set your display flag again, and just jump back to frame 1, just to prevent it from simming. And then we can go to our geometry file, find a place to save this, and call this one starter particles tut.f.bgeo.sc. And I'm going to make one change to this, because I do feel like these particles were moving too fast. So I'm going to go up to our attribute wrangle, and instead of doing times 7.5, I'm just going to do times 6. Great, so we can go ahead and save this one to disk as well, and this one shouldn't take too long. It's got far fewer particles than the other one, so we can just wait for this one. And there it is, it's done already. We can say load from disk, and that looks pretty good. The next thing to do is to merge these two together, and now we can just clean these off. So we're going to remove all unnecessary attributes. We're going to go over here to remove attributes, and we'll remove everything except ID and everything except velocity. So we're just keeping ID and velocity. Next, we can disable remove degenerate primitives and remove unused points. That'll keep our points instead of deleting them. So now if we play this back, we have the combined version, and you can see that the one effect leads into the other quite nicely, because we're using the same sort of curve to drive both of these. Now the next thing to do is to convert this to a VDB. So drop down a VDB from particles, plug this into your first input, and then we're going to go over here and change it from a surface to a density. We're going to change our point radius scale to 0.03. Then we're going to change our minimum radius to 0.1, and we're going to change our voxel size to 0.015. Go over here, set your display flag, and this will take a little moment to calculate, but once it's calculated, you'll see this density volume over here. Now, one thing to keep in mind is that your voxel size and your point radius scale are closely linked. So if you have a voxel size of 0.03 and a point radius scale of 0.03, then that is usually fine. You basically want your voxel size and your point radius scale to be the same, or you want your voxel size to be slightly smaller than your point radius scale. If you make it much smaller, you'll have a very high resolution volume and it'll take long to compute. So try to keep it to, close to this value or half. So in this case, we have it as half of our point radius scale, and that works just fine. So now we can take a look at how this looks at every frame. You can now quite easily see the sort of donut shape that we have going here. we can maybe increase our point radius scale to 0.035, make it more dense. That looks good to me. And then we can just add our point attributes at the bottom over here. So this is a way to convert an attribute into a VDB and add it to the current VDB. So over here we can go ahead and select V, so our velocity. And what we'll need to do is we'll just need to add a VDB name. Now the one that's recognized in our Pyro Solver is vel. So we're converting our V value into vel. And if you middle mouse on this, you'll notice that we actually have two densities over there. We have density and we have vel. We now have a volume that we can output. So we can just rename this null to density underscore out. And what I like to do is actually duplicate this VDB from particles over and then change its settings slightly. So voxel size of 0.02, point radius scale of 0.02, remove the density, and what I'd like to do is just have this as a velocity, because I like to also have a velocity to work with on the other side. So we can call this one velocity underscore out. Now this isn't necessary, but I do like to separate them because sometimes you want to have them separate. You know, you might want to add velocity at a certain point, and so, you know, it's easy to rather split these two up. So now we can go ahead and start on the last part of this, but we can just do some cleanup before then. So put that into a network box, go up here, put our curve particles into a network box, and then we can begin on our temperature. Now temperature is what's going to give it that glow that you see in the intro. So grab your transform node, and like we did before, drop down a polyframe. And we're not going to be using normal name or tangent name, we're going to be using bitangent, and we're going to set this to V, just like we did before. So, you know, we have our point trails on here, all of these velocities pointing outwards. So we're shooting particles away from our curve. Next we can go ahead and drop down an attribute Wrangle, and over here we're just going to say V at V times equals 2 multiplied by rand at time times at pt num. So what this will do is it will change our velocities per point each second, or rather each ticking of time. So that's every frame, it will reseed it. So now what we can do is we can go ahead and drop down a scatter node like we usually do, and we'll keep it at 1000. Or actually, let's rather drop it to 500. We will jitter these points a bit. Drop down a point jitter with a scale of 0.1. Drop down a pop network, and now we can begin on finishing up our temperature. So plug it in there, dive inside, and we won't be using scatter onto surfaces on our first input. We'll be using points. Go over to birth, and we won't be birthing too many, just 50,000. That should be fine for now. And then we can go down here to our life expectancy, and we can set this to 1 with a variance of 0.5. Then I'm just going to drop down a pop attract, just like we did before, and I'm going to go over here and once again add a 4 scale, pulling it back towards the center. 4 scale of 6 should be fine. If we play this back, those particles are living for too long. That's the one thing that we need to change. So we can change our life expectancy 0.3 and 0.1, and that looks pretty good. So I'm just going to drop a pop replicate node right after our pop attract, and what I'm going to do is just constantly birth 20 particles with a life expectancy of 0.2 with a shape of 0.05. We're going to add to inherited velocity, so we're going to inherit 0.25 of the velocity, and then a variance of 0.1 on every axis. And now what that will do is create trails for these points. Perfect. Now we can go ahead and jump up, drop down an attribute Wrangle. So we're going to create a few things. Firstly, we're going to define a gradient of color for this, and we're going to base it on this particle's life. So create a float called age, and we're going to make it equal to @age divided by @life. Now something to note about this, @age is how long a particle has lived for, and @life is how long it is expected to live for. So if you divide age by life, you end up with a percentage. So if a particle is 1 second old and is expected to live for 2 seconds, then you will have a value of 0.5. So you have 50% of its total life has been lived. So we can actually use that as a channel ramp because it's a value between 0 and 1. And we can just go over here and say at brightness equals channel ramp, and we're going to just put over here the name. We're going to call it brightness underscore ramp, and then use the attribute to drive it by, and we're going to be using the variable age. And then we can create this, and you won't notice any difference over here, but if you drop down a color, we can go over here to ramp from attribute and enter brightness. And as you can see, we have this aging of particles so that it's dimmer towards the edges. And because we're replicating particles, their ages differ, but it still adds a decent look to this. So we can go ahead now and just drop down a noise, so that'll be an attribute noise. And we're going to affect this brightness attribute. So we're not going to use additive, we're going to be using multiplicative. We're going to change our signature to one-dimensional because we're using a float, and that float is brightness. So set your attribute and make it animated, simplex. We'll remap it to 0 to 1 with a pulse duration of 0.3. So pulse duration is just how quickly our noise offsets itself. So how quickly it changes itself or evolves. So we can change our element size to 0.2. And now we have a noise on this brightness attribute. And once again, if you'd like to visualize that, it's quite easy with the color node. And now you can see there's noise on that. So now we can go ahead and drop down a VDB from particles. And we're just going to set this to a density, so a fog VDB. Change your point radius scale to 0.05 and voxel size to 0.05. Going to change our minimum radius in voxels to 0.1. And as you can see, we now have this volume over here, but we're actually going to be using something else. We're going to go over here to point attributes, we're going to find our brightness, and we're going to turn it into a VDB called temperature. And now we can remove our density, and all we have left is this temperature. So we can change the size of this 0.02, 0.02, even smaller, should be fine. So we have a very fine VDB. So we'll go 0.0075, 0.0075, and that's a very fine VDB, but that's perfect. It should look just fine. And now we can go ahead and output this as well. So we'll drop a null. We'll call this temperature underscore out. Put that all into a network box. And now we can go ahead and actually create our smoke. So jump up a level and we'll hide our setup node. Drop a dop network. Change this to smoke. We can dive inside and we're going to drop a bunch of things in here. So we're going to drop a Pyro Solver firstly, and then all of the things that need to connect to this Pyro Solver, and that would be firstly a smoke object, and then a gas resize. So we're going to use fluid dynamic, and then we're going to drop a volume source. So into your first input we're taking our smoke object, second input gas resize, and the final input we'll be putting our sourcing, so our volume source. So as you can see, it actually tells you what you're putting into each one, and then we can just output that. Now, gas resize will be the first thing that we set up, and basically what this does is it resizes your bounding box for your volume. So this is important because if you have a box that's too large for the amount of smoke that's being generated, then you have a lot of wasted voxels. You have empty voxels that are just taking up space. So what you need to do is change this dynamically. So it needs to adjust to the size of an object. So we're going to give padding of 2, and then we're going to go over to max bounds. We're going to say from object, and we're going to go and find our object. So go over to our obj setup, and we're going to select density out. And then we can actually increase the padding on every other axis. and that'll work just fine. The next thing to do will be to source in our volumes. So go over to our volume source, and we need to go find our density out and set that as our subpath. And now we need to make a few operations. So we're going to make two because we need to bring in firstly density, and secondly we need to bring in velocity. So we're going to say, which source volume are we looking for? Well, we're looking for density. And what would we like it to become in our solver? We'd like it to become density. So now we're bringing in our density, and it's being fed into the target field of density. And we'll leave it as add. We'll maybe just up the scale so it's more dense. And then we can go over to our source volume over here on the second one and change this from scalar to vector. And that is because we're bringing in our vol, and that's a vector. So bring in vol, and target field will be vol. Next, we're going to make another one and drop down a volume source. And on our first volume source, I'm actually going to change our scale of our velocity to 0.75. I'm going to drop down a merge node, and we can merge our volumes together. Now, on the second volume source, I'm going to choose velocity out, create an operation, and we're going to say vol to vol, and this time we're going to add a full scale of 1. Now the next thing that we can do is do another volume source, plug it into the third input, and over here we're going to go ahead and find temperature out, fields to match, we'll just say temperature, operation, source volume, temperature, target field, temperature, and just change the scale of this to 0.75. And finally, on our Pyro Solver, we need to set up a few things. So we'll leave timescale as is, temperature, diffusion, and cooling rate are all fine. We'll change our buoyancy lift to 0 and our buoyancy direction to 0. Combustion, we will disable because we don't want combustion. We basically just want to smoke. So we'll go over to shape as well. We'll add some disturbance, set this to 2, and we'll add some sharpening of 0.5. So this makes our density more well defined. So disturbance just adds some interesting shapes to this that doesn't really actually affect the overall look, but it adds a bit of detail. The only thing that we need to change about this is that our control field for our dissipation is set to temperature. And we don't want it to be controlled by temperature. We just want it to dissipate, uniformly. So what we're going to do is we're going to quickly go down here and disable our simulations. We're going to set our dissipation to change over the frames. Now dissipation is just how quickly smoke disappears. A high value, which is considered, anything above 0.5, will make your smoke disappear very quickly, whilst any value lower than 0.5 will make your smoke disappear more slowly. So we can go ahead and set our dissipation over here to 0.7 at frame 1. We're going to go over there and then keyframe it by pressing Alt and left click. Jump over to frame 48, set your dissipation to 0.3, Alt left click, go over to 72 and set this to 0.15. Once again, Alt and left click. So now it ranges from 0.7 to 0.15. And so we have higher densities of smoke as this goes because they dissipate less. And one thing before we continue, actually disturbance is probably way too high right now. I'm just going to set that to 0.1. And I think I also forgot to change, so field rank over here in our velocity needs to be a vector because velocity is in fact a vector. So now that we have that in place, we should be able to just go over here on our smoke object, change the size of its boundaries, 5 by 5 by 5, give it a division size of 0.04, maybe even 0.03, but I think 0.04 for visualization will be just fine. Then we can jump up a level, and what we can do is just a little trick, and that is to go over here from simulation to cache and remove this cache simulation option. So I'm just going to jump back to the beginning and re-enable simulations so I can show you what this does. So if you play this back, you'll notice that you have this blue bar that's generated, right? That's your cache, and this is caching to your RAM, your memory. Now what you can do is disable this caching. So remove cache simulation. What you'll notice is that it simulates to frame 7, right? We still have frame 7 over here, but we can't play it back. It'll need to recalculate every time we go ahead. So if we have until frame 20 simulated, it won't have all of it cached. So we can't just jump to it. Now you might think that's very inconveniencing, but The thing is, when you're simulating for a long period of time, your memory fills up. So your cache gets full and your memory gets used up. And what ends up happening is that has a compounding effect with the fact that generally your simulations are getting more complex. And you end up with very, very slow simulation towards the later frames. It doesn't completely remove the slowing down that you'll experience in simulations, but it does help quite a bit. So we can just disable our display on our smoke, and finally drop a geometry node. And this geometry node we'll just rename to smoke_cache. Dive inside, drop a dot input output. And what we'll do is just bring in our smoke. So find smoke over here, and that will be our DOP network. And then the DOP node that we need to bring in is, in fact, the smoke object. So find your smoke object, bring that in as well. And now we need to bring in 3 fields. That will be density, velocity, and temperature. So 1, 2, 3, density, velocity, temperature. And velocity we'll just make invisible. We don't need to see it. In fact, it's actually distracting if we see it. So now we play this back just to make sure that it's being brought in, and that looks fine. So the last thing to do will be to drop a file cache node. And we're going to just save this to disk, so find a place to save this. And we're just going to name this smoke.tut.bgeo.sc. Accept. And now, saving this to disk is going to take quite a while, even if you have a decent computer. It may take between 10 to 20 minutes. And another thing to keep in mind is that these files actually end up being quite big, anywhere between 200 megabytes and 1 gigabyte per frame. So keep that in mind. If you'd like these frames to be a lot smaller, you can actually remove your velocity, and you can also reduce the resolution of your simulation. But we can go ahead and save this to disk. Once that's finished caching to disk, we can say load from disk, set your display flag, play this back. And as you can see, we now have basically what our pop networks were, but as smoke. So it may look quite flat right now, but we can jump up a level, go over here, drop down an area light, and then we can also go over here and create a camera. So just Ctrl and click on camera. So now we can see basically how it looks. And as you can see, it's not very high resolution. This is basically just for visualization purposes. So now that we have that set up, the last thing to do is to just add lightning to this, and then finally to render it. So we can go ahead and hide our smoke cache for now, drop down a geometry node, and rename this geometry node to lightning. Now we can drop down an object merge node, and go find our particles. So we'll be using our curve particles out. So it brings this in over here. And we're just going to drop down an attribute wrangle. And then we're going to press Alt and E to bring up our string editor. Now, in here, we're going to remove a lot of our points. So we're going to say if rand at ID. So each point has a unique ID that's constant over time. So it's almost like a point number, except it doesn't change over time depending on how many points you have. It's constant. So we can say if rand at ID greater than 0.00001, then we'll remove that point. So we'll say remove point 0 at pt null. So that's going to remove a lot of points because we're basically using this as a percentage. So we're just going to apply and accept. And you can see that it's removed most of our points. Now we're going to go back and add another if statement. Just press Alt E again. We're going to say if rand at ID times round to int at time times 10 times fit, then in brackets rand at ID, comma 0, comma 1, comma 0.5, comma 1, greater than 0.5, Then we'll also remove the point. 0, at pt0. Apply and accept. And what that should give us is jittering of the points that we currently have. So they'll reseed every 10th of a second, and we can create trails off of those. So drop down a trail node, and we'll do 10 trail length, and then we can add, go to polygons, by group, by attribute, and add by ID. So now we end up with these lines that are generated, and what we can do now is just go ahead and drop down this lightning no bases HDA that I created, and this will be available to our patrons. They can download this file, and what this does is it takes our lines and it will convert it to lightning. We also have a tutorial series on Patreon which goes over how to do this, but as you can see we now have this lightning over here, and it's got branching as well as emission and color settings. So I'm just going to change its color over here closer to white. And now if we jump up a level, we can reactivate our smoke. And what I'm going to do over here is just drop down a Zeolite, so select our lightning, click on geometry light, give us a color of light blue. And what I'm going to say over here is that our intensity will equal 4 plus rand $FF times 2. So it'll be a base value of 4, but it'll flicker. So if you want to see how that looks, you can actually see that the lightning is flickering, and it might be a bit tough to tell in this view over here, but when you render it out you'll notice it definitely. So now we can just enable our lightning again, and what I'm going to do is to show you how to render this, because I didn't actually render this in Mantra, just because Mantra doesn't deal with volumes very well, but you can render this in Mantra if you have to, and the best way to do that would be to use this fireball shader. So I'm going to show you how to recreate it. You just drag over this fireball shader onto your smoke, go over here, you're going to make a few changes. Go over to fire intensity field, change this to temperature, go over to general, and then we're going to set our density scale to 2. We're going to go down to the bottom, change our shadow density to 3, go up here to our temperature scale, set it to 1, intensity scale to 5, and then we can just play around with colors. Once we have that, we can just drag up this black a bit, bring our blue down, maybe make it a bit more blue. Then we can go ahead and go to our render view, object camera 1, and then click on render. And there we have it. That is how you create the Thanos portal effect, and I'm going to be attaching the original file for our patrons so they can download that, so you can go through it and take a look at how the actual render file that I created was. It looks a little bit different to this. In fact, I could show you right now. So we can just save this one, and I'm going to open the other Thanos portal effect. So this is the file that I used, and I'm just going to show you how this looks when it's rendered. And this one takes a little bit longer because it's quite a high-res smokesome. And there you can see it. I'm just going to change my camera real quick. Camera 2. And we're going to jump ahead, close to the end, go ahead to render view, and we can take a look at this one. So this is much the same. There are a few minor changes, such as noise patterns, and of course I have a few extra nodes here and there, because this was the original and I simplified it down for the tutorial. But really, in the tutorial, it's basically what you need to recreate this. You can just mess around and add your own twist to it, and you should get something close to this. There we go, looks pretty good in here. We can just adjust our camera. And there you have it. Now, if you're one of our patrons, you can go ahead and download the Portal original render file, as well as this tutorial file, so that's the file that was created during the tutorial. You can also download our Flipy destroyer. You know, that's if you want that, our Flippy that we created for this tutorial, he's there for download. As well as our Lightning HDA that we created, there's a file for that. You can download that and check it out and add it to your digital assets if you want. And then we also have our blog post. You know, there's more information there on how all of this works. And finally, a huge thank you to our patrons. They really help keep this going, and here they are in our credits. So once again, thanks to all of you so much for helping us keep these tutorials going. Without you, there wouldn't be tutorials. So until next time, have a good one.